Optimization Models 2, Chapter 11, Sections 11.3 through 11.5. We're going to look at a simple minimization problem here. We have a company, it's M&D Chemicals, and it produces two products that are sold as raw materials to companies manufacturing bath soaps and laundry detergents. Based on the analysis of the current inventory levels and potential demand for the coming month, M&D's management specified certain production requirements, which we can see here. So we can see by reading here, we can see that the combined production for products A and B must be at least 350 gallons. So they must be producing the chemicals in gallons. So combined production 350 gallons at least as a minimum. Separately, a major customer's order for 125 gallons of product A must also be satisfied. The processing time for product A is 2 gallons per hour, and for product B, it takes 1 gallon per hour. And for the coming month, 600 hours of processing time are available. The production cost is $2 per gallon for product A, and for product B, it's $3 per gallon. The objective is to minimize the total production cost. Okay, so we're going to minimize the total production cost. That's our objective. And we're also told that A is the number of gallons of product A that will be produced, and B will be the number of gallons of product B to be produced. So we want to minimize our costs. So let's go back. Now that we know that we want to make a decision as to how many gallons of product A and how many gallons of product B should we make to actually minimize our costs. So let's just go back and put these into a bit more context. So the first thing we have is that the combined production for products A and B must be at least 350. So that means that A plus B must be at least 350. And that is the constraint with the parameter on the right-hand side for that assertion or for that request. Separately, a major customer has ordered for 125 gallons of product A must be satisfied. So product A must be at least 125 gallons to satisfy that particular customer. And then the processing time is 2 hours for product A. So for every gallon of product A, it's going to take 2 hours. So that's 2 8-hours spent on producing all the gallons of product A. And for product B, it takes 1 hour per gallon. So 1 hour, now there's a 1 in there, but I just write as B. And that must be less than or equal to 600 because that's the constraint we've got coming in through there. So these are the three basic constraints. The other constraints that you may want non-negativity. So the model can pick that up for non-negativity. And so what else do we have apart from those three constraints? On the following slide, we also saw that the objective function is our costs, and we were told that our production costs were $2 for gallon A. So our production cost, our cost could be $2 for every one of gallon A, and also $3 for every gallon of B. So this is our cost, and our objective is to minimize costs. So now we can actually go into Excel and put that stuff in there. The constraints I just wrote down are actually given to you there, but I can go ahead now over to Excel and put that information in. So what we have is product A and product B. And these are the chemicals that are going to be produced, and we want to make a decision about product A and product B. Now I'm gonna just highlight these in yellow. Reduces the chances of me making a mistake. So I want Excel to tell me how many gallons of product A and product B I should make. I want a decision on that so that I meet my objective. And my objective in this case is to minimize the cost. Now, we already know what the costs are. We said that the costs are going to be that 2a plus 3b. So I can actually write it over here. It's just right over here. I'll draw it in. And come for this line in here, it's going to be 2a plus 3b, and we want to minimize that. So how do we actually put that in on here? So it's just going to be 2a plus 3b. I actually add some spaces in here. Maybe don't want that, but never mind. Just insert a few spaces. Okay, so the reason I inserted some spaces into here, let's put no color in here. The reason I inserted some spaces is that the objective is to minimize cost, and the formula is 2a plus 3b, so it's going to be 2 times whatever I have it in A and 3 times whatever I have in B. And I'm going to actually put the cost in here, and I can actually put the cost in red if you like. And the actual formula for the cost is going to equal this times this plus this times this. And again, I'm just going to use sum product. And I'm going to put a comma. And on these ones up here, I'm going to put dollar signs because I'm going to copy the formula down. And whatever the decision is going to actually be true for not only my objective function, but also the constraints that I'm going to write in further down here. Okay, and so they're my costs, and now I'm going to put in my constraints. So I had one constraint, so it doesn't matter which order you put the constraints in. So we can actually say, for example, let's put in the combined production. So the combined production we have is going to be A plus B must be greater than or equal to 350. So again, I can write it in this one here. So I can just put in A plus B. Remember, the combined production must be greater than or equal to 350. So how are we going to write that in? We're going to write in a little bit higher up here. But let's write that in. So it's just going to be 1A plus 1B. And here we're going to actually write in the same formula we've got up above. So it's going to be sum product of these guys times these guys up here. I could have copied it down from above. But there you go. And I want that to be greater than or equal to 35. Maybe I should get rid of that little dot in there so it's not misleading for us. Okay, so what do I actually have in here? This is the inequality, and in here is the actual usage, if you like, and this is the availability. Okay, and this is actually 350, not 35. There you go. So that is the constraint for the combined production. So there was another constraint on the major customer. So let's just put major customer. And the constraint for that person was that, well, let's write in again. I'll write in over here. So for the major customer, we were told that for this major customer, A, the amount of product A, gallons of A, must be at least 125 because we must satisfy this customer. So how am I going to put that as a constraint? Well, there's 1A. There's just one value in here for A. And there's no values in here for B, so I can just leave that blank. What do we actually use is that amount. And for that constraint, again, it's a greater than or equal constraint. Now the greater than or equal that I'm putting in there is not going to be picked up in Excel. It's just for our own benefit, so we don't lose track of what's going on. And the parameter is going to be 125. And the third constraint was to do with time, the time it takes to process, if you remember that constraint. And that constraint basically said that the time it takes to process is going to be 2 hours for each of gallon A. So if it's 2 hours for each of the A gallons, this is the amount of time you're going to spend producing gallons of A, and it takes 1 hour for each of gallon B. So this is the total amount. This is the total amount of time you're going to spend producing gallons A and B. And we're told that's got an upper limit of 600. So now we're going to put that in here. So that's just going to be 2A plus B. And what we're going to use on that, how much time would we use on that? And we know that that time has to be less than or equal to 600. And that's pretty much it. We don't want to be trying using trial and error and actually putting different values in here ourselves and seeing the values that actually fulfill these conditions or these constraints down here. It takes a long time, so we're going to use Solver. I'm just going to come out of full screen because for some reason Solver doesn't like full screen. So I'm going to press Data, I'm going to press Solver, and I'm going to put my information in. What's my objective? My objective is my cost. What do I want to do with it? I want to minimize it. I don't want to maximize it. I want to minimize it. And let me actually just reset all this. Let me just reset everything here and do it from scratch. I'll do everything from scratch for you. So let's see. So our objective is our cost. And what do we want to do? We want to minimize our cost. How? By changing what we have in these cells here. And want to add in our constraints. So these constraints here, let's add them in. So these constraints like match up with cell reference that goes in here is whatever's in here. Inequality here, and the availability goes over here where it says constraint. Now the first two you can put in individually, but since this inequality is the same, we can actually put the first two in together. So those two are greater than or equal to these two. And Excel will figure that out. And we want to add in the last constraint. The last constraint is this. That one is less than or equal to, and over here we're going to put in this. That's okay. Make unconstrained variables non-negative. We don't want to be told we have to produce minus 300 gallons of A and minus 5 of B. We don't want those sort of results. And we're interested in linear programming. So we're going to press Simple XLP and we're going to press Solve. And that's going to tell us in here the decision as to how many gallons of A and how many gallons of B we should actually make to actually minimize our costs. And it turns out to be 250 gallons of A and 100 gallons of B. And if we do that, our cost will be at 800, and that's the minimum. And they fulfill all the requirements we have in here. So that's how quick it is to actually do a question. Once you get used to it, it actually works quite quickly. On your PowerPoints, it actually gets the answer report. If you want to see the answer report, you press Answer and you press OK. Now, if you've already got answer reports in there from before on your spreadsheet, like I have here, it's going to bring them in again. It's going to keep on adding them. So since I've got some in there, let's see what it does for this one. So it's added in answer report 2. So because I had some in there previously, it's added in answer report 2. And we can look at that report as well. The requirement that at least 125 gallons of product A be produced is not binding. So it's not binding because we're not at the limit. When you're at the limit is 125 and we're at 250. So we're not at the limit. It's only binding when you're actually at the limit. For greater than or equal to constraints like the first two, and especially this one, we can define a non-negative variable called a surplus variable. Now, a surplus variable tells us how much over the right-hand side, the left-hand side of this greater than or equal to constraint is for a solution. So in this case, the surplus is going to be 250 minus 125. It's going to be 125. So that's what a surplus is. Surpluses are possibly around when you have a greater than or equal to hypothesis. So if you have a greater than or equal to, assertion like in here, then what actually is going to happen if the use is above the minimum, then you say you have a surplus. When you have a less than or equal to inequality, like we have this one, this constraint will have what is known as a slack only if this is below the minimum. If it's at the actual limit, and this one is at the limit, that means it's going to be binding. So this would be binding. This would also be binding because even though it could possibly have a surplus for a greater than or equal to inequality, it's at the limit, so it's binding. But this one is not binding because it's not at the limit of 125. And for a greater than or equal to, when you're not at the limit, that's called a surplus. And that's going to be borne out when we look at the answer report in here. So you can see that for a major new customer, then it's not a binding constraint. The 250s, well, this is the actual usage. 350, 250, 600, so have a look at there. 350, 250, 600, that's what we actually used. And this constraint is not binding and it's a surplus because we're above the minimum for greater than or equal to inequality. The other two are binding because they're right at the limit. Okay, so basically that's the information that we have in here, and Excel does it. They set up their spreadsheet, the publisher does it as well in the PowerPoints, but they do it in a slightly different way, but they do come up with exactly the same responses as you'll be able to see from that, and they come up with the same answer report. They may have put these in a different order. It doesn't make a difference which order you put the information in. So let's move on. Special cases of linear program outcomes. There's three here that we're going to look at. The first of the three is alternative optimal solutions. So sometimes you actually get more than one possible solution to a question. And so let me actually go back to a previous question that we did over here. So do you remember this question? This one was the one about golf bags, and we were given constraints on cutting, sewing, finishing, inspecting, and we ran the model. We wanted to maximize our profit. We came up with the number of standard bags we should make is 540, and the number of deluxe bags is 252. That was the only solution for this question. Now, sometimes you have more than one solution for a question. So let me just do kind of a little quick sketch over here. So when we were doing that problem, the feasible region, I don't remember exactly what it looked like. It was something like this. So we can pick any solution anywhere in this region. And then what we did, we took the contour line, and the contour line is whatever your objective function line is in here. So along there. So because we wanted to maximize profit, we wanted to see the last point that contour line hit this feasible region. And if you keep on going through, it's going to be about there. That's the last point. It's actually going to hit the line. And we had a unique solution. We could find the values of standard and deluxe bags at this point in here, and that would tell us what the optimal solution that would maximize our profit is. And we know that solution at that point, there's only one solution, and a telltale sign of that is when I look at the sensitivity report, it actually said, if you remember, that my optimal solution, say of 540, remains the same, even if I increase the objective function coefficient for profit on the standard bags by an amount. Doesn't matter what the amount is, I can increase it or I can decrease it. So that means there's flexibility, and what that means in this case is that this contour line, even if I change the angle of it, I'll make it a little bit more steep or a little bit less steep. If I twirl it around here, it's still only going to hit at this one point. And that means there's only one solution. There's a possibility, though, that if my contour line was different, so if I actually changed, say, my profitability up here, if I changed it in such a way, let's change the color on this, let's do it in green. If I changed it in such a way that I changed the angle on it in such a way that now the last point or the last place it hits my feasible region is a whole line, then that means it's that whole line that gives me all the possible solutions. I can have any solution along that line. Excel's not excellent at actually pointing this out to you, but we can actually see. Let's go back to the PowerPoints and have a look what they say. So optimal solutions, alternative optimal solutions can occur, and that's when your contour line hits your feasible region at more than one place, and it's normally along a whole line. So the equation we looked at earlier for the objective function was this one in here, and now they're saying let's change our profit on the standard golf bags to $6.30. So let's go back and do that, because it's saying that's going to give us multiple solutions. So what they want us to do is change this in here to $6.30, 6.3, and apparently that's going to give me multiple solutions. Well, okay, let's run this. So let's go to data, and everything's already in solver, so I'm just going to press solve and wait for the solution. And I want to see the sensitivity report again. So again, can you see what's happened now? It's given us a different solution. I'm none the wiser looking at this if there's more than one solution to the problem. I just think that's the only one, unless I do a little bit more digging. If I look at the sensitivity report now, I'm going to see something kind of interesting. I'm going to see that when I look at this part of the sensitivity report, it says that I'm actually not allowed to increase my objective function by anything, otherwise the optimal solution changes. I may be allowed to decrease it, but I'm not allowed to increase it. And for the second decision variable, which is on the deluxe bags, it says I'm allowed to increase it, but I'm not allowed to decrease it. And when you see this, these zeros in here, it's a telltale sign that you've got multiple solutions. Another way I could see that I have multiple solutions is to figure out if my objective function line actually coincides with one of my other constraints. A really quick way to see it is to actually just find the ratio of this just to this, and it's 0.7. And so I can actually copy that down, get rid of those. And you can see this contour line, this first constraint has the same ratio as the contour line. So that means these two lines coincide. So that means we're going to have multiple solutions. And so this is showing you having multiple solutions. It's showing you your contour line, which is the line representing, in this particular question, the profit. Doesn't hit your feasible region at a single point. It hits it along a whole line. And what that means, you can choose any value of S and D for the standard and deluxe bags anywhere along that line. And they will all give you exactly the same optimal solution in terms of profit. They'll all give you the same profitability, but the S and D is obviously going to vary along that line. Now, that's a great position to be in for a manager, because the manager can make a decision to maximize their profit in this case based on a whole series of values for the number of standard and number of deluxe bags to make. So let's move on. How about in feasibility? What does infeasibility mean? It means that there's no solution to the linear programming problem. The Excel may actually return an answer to you that it's infeasible. And what does that actually mean to us? And graphically means that there's no region where the constraints are met. And that could be because the management's expectations are too high. So the management's expecting something that basically cannot be done. Or it could be that you've placed too many restrictions on it. That could also be by management, or it could be that it's just something is not feasible, that it's not going to happen. It can't actually work. So for the example we're looking at on the golf bags, if we add in 2 additional constraints, so one of them is that the minimum amount of standard bags you want to make is 500. So the standard bags are along here. You want a minimum of, this is about 500. So you want a minimum of 500. So that's going to give you that. And the minimum of deluxe bags you want, and deluxe up here, is 360. 360 is down. So it's going up here. So that gives you this region. And you can see these are the previous constraints that we had. The 2 new constraints and the previous constraints don't match up to give you a single feasible region. So there's no one place where all the constraints are met. So what do we do in this case? Why did that occur? And what can we do? I guess is going to be the question. So let's have a look. So basically, it could be that you don't have sufficient resources. And that's what it looks like in this particular problem that we're working on. And we could make the management aware. We don't just give up. We can make the management aware and tell them, look, this worked before you put on the constraints of requiring 500 standard minimum and 360 deluxe bags minimum. What we can do, if you really want to make 500 standard bags and 360 deluxe bags minimum, then I can actually tell you, we can actually tell the management what they have to do, what resources they're short on, and what they need to increase their resources by to make this happen. And that may be very valuable information for the management to have. And you can do it like this by using the formulas that we were looking at before. So for cutting and dyeing, if I want to make 500 standard bags and 360 deluxe bags, well, each of the standard bags takes 7/10 of an hour to actually cut and dye. So if I'm going to make 500 of them, then the time is going to be 7/10 times 500 bags. And similarly for the deluxe bags, it takes 1 hour to make each of those, to cut and dye each of those. If I'm going to make 360 of those, it's going to take another 360 hours. So if I want to make 500 standard and 360 deluxe bags as a minimum, I need 710 hours. Given that we only have 630, the difference between those 2 values is 80. So we can tell management that you had to add in an additional 80 hours of resources, of time, to cutting and dyeing. Now the second condition doesn't require any additional resources for sewing. It takes half an hour to sew each of the deluxe bags. It takes 5/6 of an hour to sew each of, it takes half an hour for each of the standard bags. It takes 5/6 of an hour for each of the deluxe bags. So the total amount of time to make that new requirement is 550 hours. They already have 600, so they don't need any additional resource. So you can go down there. And the management can actually figure out if they actually want to go ahead and get those additional resources in, and then you can rerun the models and take it on from there. But it's very useful. So how do I deal with Excel telling me that this is infeasible, what you've put up? One thing you can do is to actually drop a constraint one at a time, rerun the model, and see if it works. And if it does work and we can find an optimal solution, it is telling us that the constraint we missed out was causing the problem either on its own or in conjunction with other constraints. But sometimes just taking one constraint out is enough to get the model to work. So I'd like to just go back for a second to here. So if I take out the constraint on the minimum deluxe bags, so if I was to take out this constraint, so this constraint is along here. If I take that constraint out, then everything's going to work, because the standard bags, I want to have at least 500 of them, and that's going to be this line here. I want to be in this region here. And now I do have an overlap in the regions. So I do have a feasible region. On the other hand, let's get rid of that. On the other hand, it could be that I can get rid of this constraint in here, and just have this constraint that I want to make at least 360 deluxe bags. So this is going to be part of the feasible region now. And the overall feasible region is going to be this thing in here. So each of these constraints that we've got here and here, on their own don't cause a problem, but when you put them together, they do cause a problem. So that's what we have to keep an eye out for. We have to be very careful when we actually go through this stuff. But it's very interesting. So let's move on. How about infeasibility? What does infeasibility mean? It means that there's no solution to the linear programming problem. The next time I actually return an answer to you that it's infeasible. And what does that actually mean to us? And graphically means that there's no region where the constraints are met. And that could be because the management's expectations are too high. So the management's expecting something that basically cannot be done. Or it could be that you've placed too many restrictions on it. That could also be by management, or it could be that it's just something is not feasible, that it's not going to happen. It can't actually work. So for the example we're looking at on the golf bags, if we add in 2 additional constraints, so one of them is that the minimum amount of standard bags you want to make is 500. So the standard bags are along here. You want a minimum of, this is about 500. So you want a minimum of 500. So that's going to give you that. And the minimum of deluxe bags you want, and deluxe up here is 360. 360 is down. So it's going up here. So that gives you this region. And you can see these are the previous constraints that we had. The 2 new constraints and the previous constraints don't match up to give you a single feasible region. So there's no one place where all the constraints are met. So what do we do in this case? Why did that occur? And what can we do? I guess it's going to be the question. So let's have a look. So basically, it could be that you don't have sufficient resources. And that's what it looks like in this particular problem that we're working on. And we could make the management aware. We don't just give up. We can make the management aware and tell them, look, this worked before you put on the constraints of requiring 500 standard minimum and 360 deluxe bags minimum. What we can do, if you really want to make 500 standard bags and 360 deluxe bags minimum, then I can actually tell you, we can actually tell the management what they have to do, what resources they're short on, and what they need to increase their resources by to make this happen. And that may be very valuable information for the management to have. And you can do it like this by using the formulas that we were looking at before. So for cutting and dyeing, if I want to make 500 standard bags and 360 deluxe bags, well, each of the standard bags takes 7/10 of an hour to actually cut and dye. So if I'm going to make 500 of them, then the time is going to be 7/10 times 500 bags. And similarly for the deluxe bags, it takes 1 hour to make each of those, to cut and dye each of those. If I'm going to make 360 of those, it's going to take another 360 hours. So if I want to make 500 standard and 360 deluxe bags as a minimum, I need 710 hours. Given that we only have 630, the difference between those 2 values is 80. So we can tell management that you had to add in an additional 80 hours of resources, of time, to cutting and dyeing. Now the second condition doesn't require any additional resources for sewing. It takes half an hour to sew each of the deluxe bags. It takes 5/6 of an hour to sew each of, it takes half an hour for each of the standard bags. It takes 5/6 of an hour for each of the deluxe bags. So the total amount of time to make that new requirement is 550 hours. They already have 600, so they don't need any additional resource. So you can go down there And the management can actually figure out if they actually want to go ahead and get those additional resources in, and then you can rerun the models and take it on from there. But it's very useful. So how do I deal with Excel telling me that this is infeasible, what you've put up? One thing you can do is to actually drop a constraint one at a time, rerun the model and see if it works. And if it does work and we can find an optimal solution, it is telling us that the constraint we missed out was causing the problem either on its own or in conjunction with other constraints. But sometimes just taking one constraint out is enough to get the model to work. So I'd like to just go back for a second to here. So if I take out the constraint on the minimum deluxe bags, so if I was to take out this constraint, so this constraint is along here. If I take that constraint out, then everything's going to work, because the standard bags, I want to have at least 500 of them, and that's going to be this line here. I want to be in this region here. And now I do have an overlap in the regions. So I do have a feasible region. On the other hand, let's get rid of that. On the other hand, it could be that I can get rid of this constraint in here, and just have this constraint that I want to make at least 360 deluxe bags. So this is going to be part of the feasible region now. And the overall feasible region is going to be this thing in here. So each of these constraints that we've got here and here, on their own don't cause a problem, but when you put them together, they do cause a problem. So that's what we have to keep an eye out for. We have to be very careful when we actually go through this stuff. But it's very interesting. So let's move on to another problem. It's unbounded mean. If Excel solver returns unbounded for your solution, it basically means that you either have a maximization problem where the way it's being set up is suggesting that you can have infinite profits. And if it's a minimization problem and you want to minimize your losses, it's going to be unbounded as well. So it goes without bound. It just goes on forever. And this is without violating the constraints. So you may be wondering, how can that even happen? Well, let's have a look. This is a very simple example of a maximization problem. So let's just quickly do it here. And so it says this will be my x-axis, and this will be my y-axis, and we're going to have one here. Note first constraint, which is x, is my x and my y look exactly the same. This is x, this is y. X is greater than 2, so if this is 0, 1, 2 for x, so x is greater than 2. So I've got all the region over here for that constraint. And this one says that y is less than 5. So if I go up to 5 on the y-axis, and this is saying I've got everything down here. So basically my feasible region is this region in here. And it actually keeps on going on forever. There's no other bound to stop it. X and y are both greater than 0. There's nothing else, no other constraint to stop it. So when I'm trying to find the maximize the objective function, the way I do it is I put 20x plus 10y equal to 0, and when I rearrange that, I'm basically going to get that y equals minus negative 2x, and that's going to be my contour line. Let's do that in red, and I'm going to put a contour line of minus 2x, a slope of minus 2x, and I keep on going through here to the last point where it touches my feasible region. That's never going to happen. So there's the actual drawing out of it there, and you can see that what I actually drew out for you there. So it's unbounded. So if a profit maximization problem such as this one results in an unbounded solution, the mathematical model does not represent a real world problem sufficiently. There's something wrong with it. I mean, there's no bound. There's no bound over here. It could be like this. It could be like this. There needs to be some sort of bound over here. In many cases, the error is the result of inadvertently omitting a constraint during problem formulation, like over here. So there you go, and that's how you can get that type of problem. And you need to go back and check all your constraints to make sure that you haven't missed any out in that particular case. On sensitivity analysis, I already covered this with you in the previous video, and for the specific problem it's going to cover with you here. So I'm not going to really cover it again. Sensitivity analysis is explained here again. Remember the shadow price that we were speaking about and how it works. So you can actually go through and have a look at that for exactly the same problem we had before, and there's exactly the same answers we had. Maybe the order may be different here. It doesn't make any difference if the order is different as long as the numbers are the same. And just to add to what I said before, that the sensitivity analysis that we look at is actually looking at changing one thing at a time only. If you want to change more than one thing at a time, you don't look at the sensitivity analysis report. If you want to change two things in your model and see the impact used, the best thing to do is actually to rerun the model. Just a quick note on some other models. Now, there's some examples here that there's Excel templates included in your material that I'm giving you, and you can actually try these by yourselves. There's not too much difference in them. You may have more than one decision variable, more than two decision variables. We've been looking at models with two decision variables. So for example, we looked at a model where we're making golf bags, and we were looking at making standard and deluxe golf bags, and wanted to make a decision as to how many standard and how many deluxe we need to make to optimize our profits, maximize our profits. And so we had two decisions to make on the number of standard and deluxe bags. So if you want to continue with the examples, you can actually have more than two items you want to make a decision on. There may have been a third bag, there may have been a lower end bag, not just a standard and a deluxe. There may have been an economy bag, and you'd be making a decision on three of them. Just the note I want to make here is that the way that you actually notate the decision variables, you can use whatever you want. We used S and D for the number of standard bags and the number of deluxe bags. So we said this is S and this is D for deluxe bags. But some people prefer to just use X1 and X2 because it's quicker, it's easier, and you don't have to sit around trying to figure out a notation for each thing, like, oh, what should I put for the standard bags? Okay, S, and the deluxe bags, okay, it's D. But if I had like 15 or 20 categories, it becomes a bit of a pain to try and put in an individual letter for them. And there may be some things where the letters are going to be the same, the starting letter. So some people just prefer to use X1 and X2, but the disadvantage of using X1 and X2 is harder to identify what the decision variables actually represent in the mathematical model.